Hello and good morning. And this is Mr. Murphy's Science Classroom. And I hope you're safe and healthy sitting at home. And today is going to be about density. And density, right? We've talked about mass when we talked about volume. In the last one, we talked about measurement. We talked about mass being the amount of matter that something has. I called it stuff. And we also talked about volume, and that's the amount of space that something takes up. So when we talk about density, we're going to talk about the relationship between that mass or stuff and the amount of space that something takes up or space. And we're going to compare those together. So when we talk about density again, we're going to talk about the amount of stuff in a given space. So basically, if you think about, all the kids in a room, say there's 8 kids in this room, and it's a pretty large space. So when we look at that and we talk about the amount of space that we have and the amount of kids that are in that space. So I'm going to draw a little picture here. And if you think about our space, right, here's my room, not the best drawing. And then I have several students spread out across the room, social distancing. And I have 8 students in here, okay? And so the amount of space that I have here, right, the amount of space that I have here is my room. And the amount of stuff that I have, right, would be the number of people that I have here, those 8 dots. And so if you think about that, right, that's the amount of stuff in a given space. So we can call that population density or student population density. So when we look at this doesn't look very dense. In other words, there's not a lot of people in here. So it's not very compact in here. Now, if I take this same space and I bring in Mrs. Gillis's classroom next door, and she has 8 more students, 5, 6, 7, 8. No, I already have them. No, I have too many. But anyway, so she has 9 students. So when you look at this right now, right, we have more stuff in a given space. And so our population density, right, has increased. So when we talk about the amount of stuff in a given space, we're talking about, right, this. So we have a given space and the amount of stuff. So if we increase the amount of stuff or increase its mass, right, the object will be more dense. If we decrease the amount of stuff, so if I decreased it, right, and I started erasing some of these kids, and we decreased it, my density, right, of students in the classroom becomes less. And so now we have 4, right? Now we have 4, and you can see it's a very large room now, and we have a lot of space. So again, right, density is the relationship between mass and volume. So it's the amount of stuff or the amount of matter in a given space. And in this case, right, we were talking about a classroom. So now, how do we calculate that? Well, it's a simple division problem. You're going to, take density and divide, right, the mass by the volume, and you'll come up with the answer. We'll talk about that in a second. If you look at this iceberg up here, now the iceberg, right, the iceberg has, an area on top, and most of you probably know that, right, it has an area that goes underneath the water, right, doesn't touch the bottom, right, doesn't touch the bottom, but it has an area probably bigger than this area, more than likely bigger than this area underneath the water. So it's floating. So if you think about it, right, if it's floating on top of this, right, then something must be different about the ice than the water. And that's what we're going to talk about in the next couple of slides, because water is kind of one of the unique substances where density is a little different in water than in others. So let me get my pointer back here and we'll roll down. So density, right, is a physical property of matter, right, that can be used to characterize a pure substance. It's basically the ratio between mass and volume. I'm going to slide myself over here. And its units are grams per milliliter or grams per centimeters cubed, which makes sense, right, if you think about it, because when we talk about mass, right, we're going to talk about grams, right? We measure our units in grams. And I've got to figure out a way to get better at drawing. And when we measure our volume, right, our volume would be either in milliliters, I can't even make a good circle, or centimeters cubed. So one of those units would be down here. And so if you think about it, it'd be grams per milliliter or grams per centimeters cubed. And that's the way, we would put units with our density. And that's just based on that relationship between mass and volume. If you look over here, I have this triangle, and it has M on top, and then has D, and then V. So this is what I want you to think about when we do this. If you look at if you cover one of these letters, so if you covered M, right? If you covered M, you would be left with D and V. And if you thought about a multiplication sign, because they're right next to each other, right? That's what you would have to do to find mass. So if we needed to find the mass, but they gave us the density and the volume, we would just cover up the mass, that M, and you would see it would be D times V. If we needed to find volume, I would cover my volume, and you can see that it would be M, or mass, divided by density would equal the volume. So you can easily, and obviously if you go back and cover the D, you're going to get M over V, which is actually mass over volume, which is actually the density formula. So you see that you're able to manipulate the formula without having to do the algebra. Not that algebra is a bad thing, and you're more than welcome to solve each equation for the variable, but ultimately it just makes it a little bit simpler when you're working through problems. So in the Earth Science reference tables, and I put a copy of these in the classroom. I'm going to put a separate heading for them if I haven't done it already, right? And on the middle, left side of the middle of the front page of the reference tables, it has all the formulas you'll need for this class. And eccentricity being one we're going to use in space, gradient one we're going to be using in the next unit when we talk about topography, and we also might talk about rate of change as well in that unit. But we'll talk about that quite often. We'll talk about that in weather, and we'll talk about that in geological time as well. Density, right, is the one we're using now. It's the last one on the sheet. But if you need another formula besides this one, you'll get it from me, or it'll be on the test. So I have a question. So we have a boy named Charlie, and Charlie finds a goldish rock, and he thinks he's a millionaire. So he thinks this is gold. And how can we figure that out? Well, when we talk about pure substances, we talk about things that cannot be broken down any further, otherwise they wouldn't be that anymore. So most of our elements and our minerals are, kind of that way. They're kind of one thing where you can't break it down. So if I was to take gold and I was to break down gold, it wouldn't break down anything except for protons, neutrons, and electrons. And then it wouldn't be gold anymore. Pyrite being the same thing. So pyrite's on the left, gold's on the right. When you look at something like water, which is also a pure substance, you have to think about this. When you talk about water, we talk about H2O, right? So we have H2O. And that's a difficult two. So H2O, right? If we were to take the H's and separate them out from the oxygens, right? If we were to take these out, right, it would just be O. Or even if we were just to separate those, right, it would be H and O. And actually it would be H2, it'd be H2 or H1, two of them, or it would be O, and it would be O2. And so when you look at this, even though it's a molecule and also a compound because it has two elements in it, right, it still, right, exists as a pure substance because you can't break it down any further. If you break it down any further, it's not water anymore. And so that's what we talk about when we talk about pure substance. Well, gold and pyrite are both pure substances. So as Charlie's looking at them, right, we have to go back to our definition of density. We're going to way back up here, and it says physical property of matter that can be used to characterize, right, a pure substance, or identify, right? You think about identify, when we talk about characteristics, right, we're going to identify. So we can use it because it's characteristic of these minerals. So we're going to find density of gold or pyrite, and we're going to use that piece of gold material that Charlie found, and we're going to find the volume of it first. And if you look, it's an irregular substance, so we can't measure length times width times height. So we're going to use the displacement method from our measurement unit in the beginning, right? And if you notice, right, it goes from 200 up to about 215, and our volume is 15. Our mass obviously doesn't show it on the scale, but if you look, our mass is 289.5. And so if you do the formula, right, density equals mass over volume, you would take 289.5 and you would divide it by 15, which seems like it's going to be a pretty big number, or at least a decent sized number. So when we figured that out, right, and you do the calculations, it comes out to about 19.3. When you look at gold and pyrite, right, 19.3 is gold and 5.0 grams per milliliter is pyrite. So Charlie does have gold. However, is he really a millionaire? If you think about the amount that he actually has, right, the mass of the material he actually has, right, he probably doesn't have enough to be a millionaire. Maybe, $10, $15, $20,000, which is still a lot of money, but it's not a million. So he's not a millionaire, but still, it's nice that Charlie actually had gold. Now, when we talk about substances in phases, water, right? Water is an exception to this rule. And the rule is all substances are most dense in the solid phase. And that is true with most elements, except for water, right? Except for water. Water is less dense. And how do we know that? Well, because it floats on top of the water that it's actually made of. So if it floats on top of the water, then it must be less dense than the water is that it's sitting in. And similar, like oil on top of water, and how the density of air, changes, and the air ends up moving up when it's heated because it becomes less dense, right? So the ice floats. Now, ice has different densities too. So, like, even though we label it as 0.5, and that's at a standard temperature and pressure, right? We label it as 0.5. It actually could be 0.2, 0.1, 0.9. And the difference would be is where it actually sits in the water. So sometimes when you look at ice will float where it is. This is about 50%, right? So this would be about 0.5. If you had, where the ice was actually floating a little bit lower in the water, right? So a good majority it was lower, right? The density may be greater, right, than 0.5. So like, if I was to take a guess, I would say, put this in that 0.2 range. If it floats, kind of above the water, almost like a boat, right? An empty boat, then it would, your line would be here, and it would be, a lot less than 50%. So it'd be like 2 or 3%, 2 or 3, or 20 or 30% is above, below the water, and that's the way you do it. So if it's down here, right, it would be the same density as water, pretty much, or very similar to it. So it would be density of 1, which is 100% below the water. And then if you look at, if it was a little bit above the water, then it could be 90 and so on and so forth. And 50%, right, above the water would be 0.5. So that's kind of how density works within the, the water. I'm going to switch back over to my thing here. And I have to delete this because otherwise it'll travel with me. So this used to be a video here, and I removed that because I do some density tricks of my own. But again, identifying using density, remember, right, the substance, right, every substance can be identified using that. We know what gold is, 19.3, so we can actually figure it out if it's gold or not. This is how they do forensics. So if they want to find out what's at a crime scene, right, they can use density and specific gravity to figure those things out. And they do that quite often. Now, this is the other end of density, and this is the last slide I have for you today. Density of a pure substance remains the same or constant unless temperature or pressure change. So you have to look at it a couple of different ways. The first one is this goes both ways. So it says temperature increases, but we can also say temperature decreases. So the opposite of this works as well. As temperature increases, density will decrease. So if you think about what happens to an object when it's heated, right? An object will expand. So when you look at, if you have a square, and I'm going to start my drawing again, see if I can get this right. But if you look at a square and you have, right, a certain space or volume, right, and you have a certain density, we're going to put my objects in here, right? So this is my stuff. So I have these 5 dots are my stuff, and this is my volume. So if I heat it up, right, I'm not adding anything to it, right? I'm not adding anything to it, but I am, right, moving this out, right, in all directions, right? So this is expanding. So as this expands, and I'm going to show you in a second if I can actually do this. when something expands and gets bigger, right, its volume changes. So if I drew my square, I'm going to do the best I can here. If I drew my square outside of where the expansion occurred, right, now I have a big space, but I still have not changed my mass. So if you look at the formula, right, mass over volume, I have not changed my mass, but I have changed, right, my volume. So my lower number, right, my bottom number has gotten bigger, but my top number has stayed the same. So as you're looking at this, right, density has decreased. It's kind of like taking those 8 people or 9 people that I had in the first classroom picture and taking them out of my classroom and bringing them down to the gym. And they'd be a lot more spread apart. It would be a lot less dense population-wise, and therefore less dense. So it's kind of a cool way of looking at it if you think about it that way. So if temperature increases, right, the density will decrease. Now, when you take something like, let's take a balloon. If you take a balloon and you fill it full of air, and you take that balloon and you stick it in the freezer, right? Now you're cooling things down. So it's the opposite, right? So we're cooling things down. So our temperature is decreasing. So what happens is those molecules, right, will contract inside the balloon, and therefore the balloon will shrink. Because the only thing holding that balloon out is the air molecules, right, being hot and pushing out all over the balloon. So now we bring it down in, and the balloon will look compressed. It'll actually be like, wrinkly. But then when you take it back out again, it will blow back up again. Well, it'll appear to be blowing back up, but it'll just be the molecules will start moving around faster, and they'll push the balloon back out again. So that's one of the things when you think about temperature and density, right? You can think about a balloon, putting it in a freezer and then taking it back out again. And that'll show you both ways, and it's very easy to do. So try that at home. That's a good one to try at home. Now, if pressure increases, density will increase. So think about the same balloon. So if I take that balloon and I increase and I squeeze it down, or even a beach ball, if I squeeze it down, I'm squeezing. So I'm bringing that the sides or that volume. So I'm squeezing the volume down. So I'm making the volume less, but I'm not changing the amount of stuff inside. So I'm not changing the amount of matter inside. So I'm squeezing it down and I'm making it smaller. So my volume is getting smaller, right? But my mass is staying the same. So the bottom number, right, is getting smaller, but the top number is staying the same. So it's staying higher. So if you think about it, if you divide, the top number by the bottom number, it would be greater. I can look at it in terms of math for those of you who are math-minded. And I use these numbers in simple numbers because I want to keep things simple. So if I take 10, right, and I take 5, and I'm not going to put the units here because it'd be a little bit more difficult to draw the actual numbers or the actual letters here, just for sake of making this not as miserable for me. So 10 divided by 5 is 2. Okay, so we have this math problem. So this is our mass on top and our volume on the bottom, and it equals 2. So if I take my mass and I keep my mass the same, right, but I increase my volume, so I'm making my volume bigger, right? So it's like taking the people out of my room and bringing them down to the gym and making my volume bigger, but not changing the mass at all. So I move this to 10. So if you do the math on this, right, this equals 1. Right, 10 divided by 10 is 1. So 2 to 1. So my density will decrease. And vice versa, right? If I take and I shrink my volume down, right? I compress my volume, but I don't change my mass, right? Density will go up. So this is kind of an easy way to look at it. And you put those numbers up there and it's very easily seen, right? What happens, when temperature and pressure do their thing. And so that's all I have for you today. I hope you enjoyed it. There's some questions after this, on your sheet that, go over density and density problems. Some of them may be a little bit more difficult than others. If you have trouble with them, please give me an email or shoot me an email, and I will be more than happy to put some kind of video together for that. So again, be safe and hope you're healthy and have a good day.